Okay, we're recording. Welcome to the evening of Python coding. My name is Jacob. We've been having this meetup for over 6 years in the Austin area, but we extended to DC during the pandemic. So now we're having it both for Austin and DC communities. Um, each month we present a different library or a set of tools for Python, and we try to bring in expert or a local person or a local expert who knows the library, used it, and we show a short demo. Today we have a demo that may be much longer due because this library was developed in Austin for a long time. I knew about it many years by now, but it is good that everyone knew about it. It's called Numba, and Stan Seibert is one of the Numba developers. He will talk about Numba and explain it much better than me. It makes Python faster. Go ahead, Stan.
Awesome. Thanks. I'm glad I have a chance to talk to everyone here. Yeah, and that summary is pretty much it. Numbers for making Python go faster. It's a project dates back to 2012, but I would say in its current incarnation kind of came into existence around 2014. But compilers take a long time, and so at some days it feels like Numba's just getting started, even though it's 7 years old. So 7+ years old. So anyway, yeah. So I'm excited to talk to you a little bit about it. So here's the Numba homepage. I would encourage everyone to start here. If you want to learn more about it, we have an example tutorial on learning Numba in 5 minutes. But let me just set the stage before I fire up the notebook. Actually, let me get that started loading. And while that loads, I can do a little intro. So there are lots of ways to speed up Python, and Numba is just part of a broader toolbox of that. So I like to describe Numba as sort of a couple of things. It is a just-in-time compiler, which means it compiles things right when you need to run it, not ahead of time like something like GCC or Clang or your sort of traditional compiler. It compiles just before you're about to execute. And then if you call the function again, it's already compiled. It doesn't have to do it again, but it waits. So it doesn't compile things you're not going to run. It's a function compiler, so it is designed to compile whole Python functions and other functions that those functions call. It's not going to compile your whole program. So there are some approaches to this problem that will compile an entire program, or will compile bits and pieces of a function or something like that. The Numba has to compile an entire function. The second or the third thing is it's a type specializing compiler, and what that means is that the way it gets speed is it looks at what data types you're using in the function and generates machine code specifically for those types. And that helps a lot because Python is very dynamic. And so it can be, Python, when it doesn't know if you're going to be adding a list or a number or whatever, has to do a lot of work to deal with that dynamicness. If we can look at the types and say, oh, you're just adding numbers, then we can just generate machine code that just adds those numbers up. And then that's actually probably the best summary of things. The other thing I do want to mention is Numba, as the name might suggest, is very numerically focused. It's not necessarily going to be super helpful for compiling like web applications or that sort of thing. It's really aimed at numerical code. I'll show you partway through a Twitter thread that we just recently hit 5,000 followers on Twitter. And we asked, what's everyone using Numba for? And we got a whole bunch of scientific researchers telling us about really interesting stuff that they do with it. So let's jump over here. So on the homepage, there's a try Numba button.
Before you launch, so Numba comes from an abbreviation of number, like kids say num.
Yeah, I think so. I think Travis Oliphant named it. Probably, I forget the history. It predates me. So I think that was the idea, is that it was supposed to be kind of like number, like numerical. But yeah, I don't entirely remember the origin of it.
Yeah, but it's like
I do
number.
really like the logo.
It's like number.
Yes. Okay. It is. You pronounce it like number, just with an A at the end. Yeah. So let's go check out so we have a whole bunch of example notebooks that are linked off of that page, all running in Binder. Binder is a great tool for doing, tutorials and things just on the web. You don't have to install anything. Obviously, you can install Numba on your own machine, but this is just kind of a nice zero installation way to get things going. So let's talk about some basics. So let's first, Numba has a fairly simple interface. At its absolute base level, you may only need to use the JIT decorator and never touch a single other thing in the Numba API. That is, by design, we want it to be as simple as possible for getting started. So I'm using Numba version 0.54. So let's take a function. So I said it's a function compiler. So we're going to have a function here that does some kind of arbitrary numerical stuff just to create some work for the interpreter. And the only difference between this function and the function that, and a compiled function, is this decorator. So we put the JIT decorator above the function, and what that does is that when you call the function later, that allows Numba to intercept the call, look at the types of the arguments, look at the body of the function, analyze the whole thing, and figure out what data types are used through the entire function. Then what it will do is generate sort of an internal representation of your function. It's called IR, and it will then pass that off after some transformations. It'll pass it off to a library called LLVM, which might as well jump over here. LLVM, if you may not have heard of LLVM, but if you've ever used Clang, which is now the default compiler on Mac OS, Clang is built on top of LLVM. LLVM is a great library for building compilers. And so Numba takes advantage of the fact that we don't have to build the entire compiler. We just have to build sort of the front of the compiler that understands Python, and then passes the some low-level stuff off to LLVM, which can generate machine code for us and do a lot of those things. So we're going to run this. In case you're wondering, no Python equals true. This is actually the main way we tell people to use this. Numba had historically had ways to do partial compilation, which generally doesn't do what people want. So we really say, we really suggest this option. What this says is basically, when compilation is done, all the Python calls have to be gone. It has to be pure machine code. We don't want to jump back into the interpreter or do any stuff like that, because if you're using Numba, you want it to go fast. So you really want to, and if Numba can't compile it, and Numba can't compile everything, you want to know. So this will generate an exception if it can't compile your code. So let's generate some dummy data. So this is just a 10 by 10 matrix, and we're going to call our function. And this call right here, this is when actually the compilation happened. When I called that, it intercepted the call and actually did the compile for the first time. So one of the things that's important to keep in mind with Numba is that if you're measuring the speed of your code, the first call is going to be slow because that's when the compiler runs. All the subsequent calls will be fast. So it doesn't make sense to compile a function with Numba that you're only going to ever run once. You're going to want to compile functions you use a lot. Actually, if the function is really long, you may want to compile it even if you're only going to call it once. I should correct myself on that. But you can end up with very short functions where most of the time is dominated by compilation and you don't get any benefit unless you call it again. So we could call it again with a different array, and that you can see actually went much quicker. So let's time it. So let's time how long this takes. So time it's going to run it a whole bunch of times and get some stats on that. Time it's a great function when you're doing just kind of micro benchmarking like this. Okay, so every call of that function takes about 1.5 microseconds. So one thing to note is that every Numba compiled function has an attribute on it called pyfunc. This is the original function. This is the uncompiled function that runs in the interpreter. So if you ever have a Numba function, you want to reach in and grab the original Python function, you can do it through this attribute. So this is a good way to check that the answer when we run compiled is the same as the answer when we don't compile. So no exception was raised. So we are getting the same answer both ways, which is good. Numba's test suite is full of stuff like this because we always want to make sure that we are giving you the same answer with or without the compiler. So now let's try actually running the original uncompiled function. And there we go. So that uncompiled function, now that function was kind of arbitrary, but you can imagine if you have a function full of loops and math, in this case, that function took 23 microseconds. So Numba made it, whatever, so 15 times faster. So that's actually fairly typical we see for this kind of function where you have a for loop doing some math. And a lot of code looks like for loops in math. And so you can easily get 10x, 20x, 50x speed ups with Numba when you need to write that kind of code. Now, we'll talk a little bit later about Numpy, but one thing I do emphasize for people is that Numba is really designed to work with Numpy. So the first thing you should do if you're writing numerical code and you want it to go fast is use Numpy. Then once you're using Numpy, then if you want to go even faster, then Numba can help you. But if your data is not in sort of regular numbers or arrays of numbers that come out of NumPy, Numba is going to have a hard time helping you out. So you could, for example, implement this function just using pure NumPy, because we were doing operations on this array, and instead of writing a for loop, you could write this array expression. So this is going to take the array we pass in and add it to an array that's we've done some other computations on. So this is nice, and this is why NumPy is great, is you can shrink this entire function here down to one line. However, NumPy doesn't have all the tricks that Numba does. So if we benchmark the NumPy version, we'll see that it is definitely faster than the pure Python version. So that's good. That's why NumPy is good. But it's also quite a bit slower, because this was almost 10 microseconds. It's still actually quite a bit slower than Numba's version. And the reason for that is that what NumPy has to do when it's executing this expression, you can see all these nested operations, it's having to store intermediate results in another array. So when I call NP diagonal on this thing, it makes a temporary array that then it calls the hyperbolic tangent on, and then that puts out another temporary array, and then it does the sum, and then it finally adds that to A, and then that all goes into yet another array and then gets returned. So all of those temporaries, which for technical reasons NumPy has to make because it has to return an answer to every step of this calculation, Numba instead can just fuse all that together into one very compact expression. So that's how Numba can sometimes beat NumPy. Because NumPy is also a lot of compiled code in it, so it's not, compilers aren't magic, but they can help you skip over some complicated stuff. So it's important to note that Numba doesn't run all Python. It's really focused on numerical Python. In the reference manual, we actually have a list of all the Python features we support, which has grown over the years, but we're not going to ever add everything, because there's some features that aren't really useful for numerical algorithms. So I would strongly suggest you take a look at this page, and there's an associated page also for NumPy features, to make sure that the thing you're trying to do is actually doable in Numba. Because you're going to have a bad time if you come at this and you're like, okay, I have all these classes and I'm doing all this string stuff and whatever, and then nothing compiles and it's just, it becomes a big headache for you. It's really good to be able to tell when is your code applicable to Numba and when isn't it. So here's another example, but stuff you would do in Python does work, like tuples. So here we can write a function that we're going to convert from spherical coordinates to Cartesian coordinates, let's say. You can return a tuple, just like you would in Python. This function will be compiled because it's decorated with JIT. And then this function is called from another function here called random directions, which is going to pick some random directions and then do some conversion from spherical to Cartesian coordinates, because you can pick the random directions in spherical coordinates easier, but you might need them in Cartesian coordinates when you're done. So these two functions will be compiled. And the great part is that when you call this compiled function from another compiled function, Numba can use some of the other tricks LLVM has. So like, for example, calling a function from a function has some overhead. It takes some time to do that call at the machine code level. So for small functions, like this isn't too complicated, LLVM will actually say, oh, rather than make two functions and call them and all that stuff, I'll just copy paste literally this code into the thing that's going to use it. So right here, this call gets replaced with the contents of this function, and then compile and optimize all of that together. And that can give you even more speedups. And all of these tricks are done by standard compilers for C and Fortran and all of that. But now we have access to them in Python. And so that's very cool. And again, we can run it here, and it compiled it, and did all of that stuff I was just describing. So we like to joke that in some sense Numba is letting you write Fortran with Python syntax, but that's not a terrible way to think about it because it's really the use cases are very similar. So I'll stop there if there are any questions before I jump over to NumPy Notebook.
People are shy sometimes, but
that's all right.
I always.
So I should say, oh, go ahead.
I always have questions. So it's like, can you go back and show the JIT decorator? So there's some parameters there. Like which ones?
Yes.
Yeah.
This is pretty much the only one you're going to worry about for most things. This just says if you can't compile it, if you can't get rid of all the Python overhead, raise an exception and tell me rather than try and halfway work or something like that. It's really a historical artifact. Honestly, if I could go back in time, I would make this the default, and then you would just write that.
Okay, what happens if you don't? If you just do this, what happens if you don't? So this is acceptable, correct?
Yeah. So let's say, for example, I'm trying to think of something that won't be supported. So let's do. So let me import, OS, and I'm just going to do something weird in here because we don't know what OS does in here. So I do that. Nothing bad happened yet because I haven't compiled the code yet. But if I try and do this, I get an error. And it says unknown attribute. Basically, this is what we call Numba a typing error. So the only way Numba can work is if it can analyze the function and find all the types of everything, and it actually knows what to do with those types. So in this case, Numba does not have a optimized version of the OS module. So it looked at OS and it tried to look up this function, which gets the current working directory out of the OS module. And it said, I don't know what the type of that is. I don't know what that returns. I don't know what to do with this. So it raised this exception. So that's what you want to have happen. Actually, let me see. I forget what the actual default is. So if I do this, and then do this. Okay, it is complaining. Good. We made this a warning. Okay. So if you don't include the NoPython, what Numba will do is it will go through this function and go, oh, I don't know what this does, but this is a for loop with numbers. I can compile this. And it will extract out the loop, compile the loop, and then you'll get a partially compiled function. That sounds great. That's usually not what people expect or want. So now we've made it actually throw a warning pretty loudly to let you know that that's what's happening. But it will still run. So you can see here I still got my answer. So rather than have that warning go by and maybe you don't notice it because you're not looking at your screen or something, we instead advise people to do this. At some point in the future, I think we will make this the default, and you'll have to opt into the old behavior. But we're an old project, so we try to maintain backward compatibility as much as we can.
Okay. Well, thank you. But that's a good sign. Even if you don't remember everything, you just put this JIT decorator without any parameters, and if you have a simple enough function that is good, it's probably going to work nice.
Yeah.
Okay.
So, quick question.
So, yeah.
So this is maybe beyond the scope of the presentation, but what is the problem with partially compiled functions? Is it just that you're paying overhead in areas where you may not be expecting to or wanting to?
Yeah, where we end up, so people surprising themselves. So for example, they might have a function that runs pretty fast, and then they make a change that they don't realize the implications of. Now this they probably wouldn't do this, but if they, for example, wrote that code inside of this loop, now this whole loop is not compiled anymore, and suddenly their code will slow down by a factor of 10. And they'll get very confused. And then we get an issue on the issue tracker. Whereas if that option was set, so if you do this I think will still run. Let's confirm. Yes, it still ran, but you're getting absolutely no speed up at all, and you may not realize it unless you are very careful about your benchmarking. So that's why. It mainly was about predictability. It turned out that being too magical can sometimes be a downside.
So something down the chain, it like downstream is basically affecting everything upstream in this case. Yeah, that makes sense.
Yes. Here it was easy to spot, but if this function called a function, which called a function, and way down at the bottom, you did something that we couldn't compile, it would percolate all the way up, and then you end up with this function not compiling very fast either, and then are very confused.
Cool. Thanks.
Yep. So I mentioned NumPy support. One thing I wanted to call out is that the way NumPy is written, there's not an easy way for us to directly call functions inside of NumPy. So the way Numba supports NumPy is we actually have special optimizable versions of many of the NumPy functions that many contributors to Numba have written over the years. So that is why there's a separate page that supported NumPy features. So
before you want
list all of the functions we support.
Stan, before you want to just tell them a bunch of things about NumPy, because some of the people you lost them the minute you said NumPy.
Yes. Okay. Yeah. So NumPy is a very old library that is specifically for working with arrays of numbers at arbitrary dimensions. So it can be 1D, 2D, 3D, 12D. It's a really great library for working with numerical data, because usually if you're working with numerical data, you have a lot of it and you'll organize it into some kind of a matrix or a higher dimensional array of some kind. And the reason why NumPy is great is that it is a huge toolbox of functions for working with arrays. So if you want to apply math operations to every element of an array, or if you want to do like linear algebra, like matrix multiplication, I advise people, if you do anything with numbers or math in Python, you really want to take a look at NumPy, because it's a great tool. NumPy, like many other Python packages, is a compiled extension. So it actually has C and Fortran code in it that has been pre-compiled for you to do all those operations quickly. So for many things, NumPy is going to be way faster than using pure Python, and is in addition to making your code shorter and easier to read, it will also run faster. But NumPy doesn't have everything you want to do. And so if you look at the toolbox of things that NumPy offers and you're like, I don't find the function I want, there's, sometimes you can find these on Stack Overflow. People can find really clever ways to string together 5 NumPy functions to do the thing they want. But one, that can actually be really hard to read. And 2, that isn't as fast as maybe just you wish you could write a for loop that does the thing you want to do with the array. If that's the case, and you write that for loop in regular Python, it's going to run super slow. So that's really painful. But you can use something like Numba to implement that loop, or implement that custom function that you wish NumPy had, and get something that's basically as fast as if it came with NumPy. And that's really the power of combining Numba with NumPy. You use NumPy for all the standard stuff, and then we get to the thing that's not in NumPy, you can just write it in regular Python syntax, apply the JIT decorator, and get something that's as fast as if NumPy had provided it. So one thing to note that, I mentioned that Numba is a type specializing compiler. And what that means is in NumPy, when you make an array of numbers, there are different kinds of numbers. There are different sizes. So sometimes you can store a number that's 1 byte or 2 bytes or 4 bytes. You might store floating point numbers, fractional numbers, or you might be storing integers. Every one of those options is a different type. And in NumPy, they're called D types for, I think, data types. And one of the things that Numba can do is, when it analyzes the arguments to generate the compiled function, it will look at the D types and will generate a custom version of the function for the D types you passed in. So if you call it again with a different type of array, it will generate a new version, and it will keep all of these in memory. So every time you call the function, it basically goes to a little table and finds the most specialized version of the function for the arguments you gave and calls that. So you're always getting the fastest implementation, even if you call this sometimes with floating point numbers, and sometimes you call this with integers, sometimes you call it different size integers. We're always generating all those custom functions. And this is another way that sometimes we can beat NumPy, is because NumPy has to do all this ahead of time. So they have to decide, when they make the package, which types are you likely to use, and they make good choices there, but they don't pick everything. And so if NumPy looks at your argument and can't find a precompiled implementation, it will actually have to convert your data and then call one implementation it does have. Numba, on the other hand, will generate the implementation you need on the fly. And that is super helpful. So here, for example, I can call this with 16-bit integers and 32-bit floats, and we'll even specialize on how your array is laid out. So there are different ways to lay out arrays, and we'll generate custom code for different layouts to be even faster. And so the main thing to note here is that this Numba function has 4 different copies have been generated that are specialized for different kinds of inputs. And again, this is all behind the scenes. You don't have to know any of this is happening. You can just call the function and know that Numba is doing behind the scenes what it can to try and generate the fastest possible code for what you're sending it. So I think I'll stop there. I don't want to overload people with too much stuff, but honestly, the biggest takeaway here is if this at all sounds useful for the kind of work you do, go check out the Numba homepage. Go click on Learn Numba in 5 minutes and read through this. There's a lot of other things that Numba does. We actually can compile code to run on the GPU if that's something that's interesting to you. We've been doing that for a long time. We can generate parallel code. So if you wish you had a for loop that ran in multi-threaded parallel mode, Numba can do stuff like that. You have to opt into it. But there's a lot of stuff in here that you can do with Numba. So I've just shown you kind of the absolute top level.
Whoa, the GPU is interesting.
Yeah, that's kind of how I found my way to Numba. Is before I worked at Anaconda, I was a particle physicist using GPUs to accelerate stuff. And then when I found out about Numba, I was like, man, I wish I had this during my research because I would have probably written less C++ code.
So interestingly enough, and this is a relevant question for me specifically, but do you still support Python 2 or did you stop supporting?
We dropped Python 2 when it officially was deprecated some years ago. So you'd have to go to a pretty old Numba version to find Python 2 support.
How old? Like 2 years ago?
Yeah. When did I don't actually remember. You have to go check the change.
2020. 2020 was dropped. But
let's see.
But the old version is like pretty bad or still working?
Python or Numba has changed a lot. Yeah, so I guess that was when we dropped the code.
Here, remove Python 2. I saw this version still before that. I saw remove Python 2 before.
Yeah, this was
in January 2020.
Yeah. So yeah, okay, that's not bad. That that is only geez, that seems a lot longer ago than it is. Yeah. So honestly, we kept Python 2 a lot longer than I thought we would.
Okay, good news.
Now our minimum requirement is Python 3.6. We're roughly following the deprecation schedule of NumPy since we're used with NumPy all the time. So when NumPy drops a Python version, we will too.
Okay. Any more questions by anyone? By the way, machine learning folk, you'll need to know those tools, NumPy. Those who are learning to be machine learning, you'll have to learn how to work with NumPy and probably with Numba in the future. I hear it more and more and more throughout the years.
Yeah, I would say definitely where Numba really shines is in a very specific scenario where you can't find the thing that you want built into the library and need to kind of make your own function, but you still want it to be fast. Whenever possible, using the built-in stuff from NumPy or TensorFlow or PyTorch or whatever is going to be the best experience. But when you hit the wall and you're like, I just need this custom function that does a thing, this is a great tool to reach for.
What about functions where you actually need only part of them? Like, let's say I have a function that is in a library that Numba does not support, but I need to accelerate many things before I get there and after I get there, and like it's still they're wrapped up in the function, and I just want to escape with that specific call. Is there any escape or something that will make it more easy?
Yes. Yeah. So we did add something. I forgot how long ago. Where is it called? This is escaping me. Hold on. Where is the object mode context manager?
Take your time. It's not under pressure.
Yeah, no. Sorry, I slipped my mind where it was in the manual. So we do have so one approach to that is to try and reorganize the code so that all of the sort of numerical, computationally intense stuff is isolated in one function. That is sometimes not feasible, but if you can do that, that definitely also makes it easier to swap in new implementations. Like if you want to support the GPU, then you have one function you can just replace the GPU version. But if that's not feasible, we have a escape hatch here, which basically lets you go back to what in Numba lingo we call object mode, which is basically the Python interpreter. So you're back to Python objects and not machine code per se. So this construct will let you basically in the middle of a compiled function say, hey, everything under my with block here, I'm going to run in the interpreter. So this is like, often this is used for callbacks where you're like, I'm doing a long calculation and I want to go update a progress bar, or I want to go update a GUI or something else that isn't numerical, it's not optimized, you don't care, you're just going to periodically go ping something. This is a way to do that.
What about the parallel stuff? How does it work?
So what the parallelization does, this is actually a optimization pass that was contributed by some developers at Intel a number of years ago. And what it does is it requires, it doesn't work for everything, and it requires you to think about how the parallelization. So it's not going to just take your code and magically make it run in parallel, but it unlocks. So it's a new argument to that decorator that is says, okay, I'm going to do multi-threaded stuff in this function. And once you've enabled that, then you have access to a new kind of for loop, which you may have seen from another library. I forgot which one we borrowed this idea from. But instead of range, you write p range. And p range and range semantically mean the same thing. But one extra bit is this is saying this loop is safe to run in parallel. What that means is that every iteration of this loop is independent of every other iteration with some minor exceptions. Here you can see we're doing an accumulation step. We can see that reduction and we can make that safe for you. But there are lots of other code patterns where you can create race conditions. Like if different iterations of your loop are going to write to the same slot in an array, that's a race condition and you can't use p range. And so, but there are lots of cases where you're going to, every element of an array that you're writing is independent of every other one, and you can do them all in parallel. In that case, using p range is great because what that will do is tell Numba, okay, we'll start a batch of threads in the background equal to the number of CPU cores we have, and then we'll chop up that array into chunks that we'll hand off to each of those threads, and they'll all run in parallel and then sync up at the end. And so there are other things that parallel can do. It can actually analyze array expressions. So if you're saying like an array plus an array times another array, doing stuff like that, a lot of times those are also embarrassingly parallel kind of operations. And so Numba can also, if you turn on parallel, will go analyze those array expressions and make them parallel as well. But a lot of people, honestly, if they use parallel, they're using it because they just wanted to write a parallel for loop. If you're familiar with OpenMP from C and C++ and Fortran, this is kind of like that idea.
Okay. Yeah, powerful library. Does a lot of things with a name that resembles Numba. Okay. I would ask some questions for the audience. Please don't be shy. It's like, no questions? Nah. There must be a question though. It's just they're just shy.
I have a question.
Yep.
Yeah, I have a question. In addition to the docs that you're just showing us, is there any other place to learn more about Numba and to use it and everything?
Yeah, so there's we have linked up here actually some talks and tutorials that we've given in various venues over the years for different kinds of audiences. So for example, if you're curious about the GPU stuff, we've taught for a number of years at various conferences a GPU tutorial using Numba, which we put all the notebooks online. So you can come, it's linked off of that page. And we have notebooks on, how you use this for the GPU and stuff like that. So these are good if you're interested in more of a talk format and less of a reading a page top to bottom. Check these out. We have video links on all these, and not all of these are by us, which is great. We love seeing other people talking about Numba and sharing their experiences with it. So, yeah, I think this is a good resource here.
Awesome, thank you.
I see a question in chat. So what does impede do?
I'm not sure what that was in reference to. Impede. Maybe I said something
NP.
strangely.
I think it's the number NP, some sort of function call.
Numpy. Is that?
Yeah, well, Numpy we already handled. We talked about this. This is probably a question that was asked long ago.
Maybe this is in reference to OpenMP.
Oh, OpenMP. Oh, that's okay. Yeah, I didn't say that very clearly. That's what it is. Yeah, so OpenMP is an extension basically to a number of compiled languages. So you can OpenMP. So we just go find it real quick. OpenMP. So it's a standard for adding to a programming language like C or C++ or Fortran parallel execution. So it does this basically via special additional information you add into the code. So if let's say you're writing C++, which is the one I'm more familiar with, you might write, a for loop in C++. If you want to use OpenMP to make that for loop run in parallel, you can put a little, they call it a pragma. It's basically a little thing right above the for loop that says, hey, this loop is parallel. Maybe you might say, hey, I'm going to do a reduction on these variables or something. You give the compiler just a little extra info. And as a result of giving the compiler that extra information, it can then take that code and automatically run it multi-threaded. So OpenMP is a really cool thing for used a lot in scientific computing and other things for, and it's available for C++, C, and Fortran, and maybe other languages too. But those are the most common ones. So if you use Fortran and you are wanting to do stuff in parallel, you should go look up how OpenMP works in your Fortran compiler, because it's very cool.
More questions? Okay.
See one here. Is there any limitation to parallel execution? Basically, the basic limitation is you need to be able to avoid the race conditions in the way you organize it. So some algorithms are, as written, are not a good fit for parallel computation because like every pass through the loop depends on the previous one. And so if you can, but if your algorithm can be expressed in a way that does have independent parallel pieces, that's going to be the best thing. Now, the other thing I should note is that the parallel execution is sort of in this very multi-threaded p-range kind of sense. It's not what I would describe as sort of full-blown task parallelism, where you have like different tasks that have nothing to do with each other and there are dependencies between them. If you want to do that kind of parallel execution, that's something I would look at Dask for, which we also work on at Anaconda. But Dask is another great library. You can actually use them together, so you can do the sort of array, core numerical stuff in Numba, and then the task parallelism you can do with Dask. And so this is another. If you're doing more of that kind of free-form parallelism, I would say Dask is a much better tool. Also, it has built-in parallelism, distributed and parallel versions of NumPy pandas and other scikit-learn and other things. So if you wish you had a parallel data frame, Dask is a good thing to check out.
Yeah, they presented this year, I think. Yeah, this April, I think. They gave presentations about Dask. There's a company in town also, one of the main developers of Dask, Matthew Rocklin.
Coiled.
Yeah, so Coiled he started another company that's called Coiled, and they have Coiled is also another library, but it's kind of like an extension of Dask. There are several other extensions of Dask now, like Prefect. We gave a demo last month about that. but Dask seems to be a a base library now for other libraries that build on top of it. Yeah.
Yep. Yeah, but Dask came about at Anaconda just a few years after Numba was created, and now it's obviously much bigger than Anaconda, which is great.
Okay. I'm not sure how bigger it is, but it's like it has a lot of use cases. Anaconda, although it's like if you talk about what Anaconda does, the Python distribution is I think it's the most downloaded is Python distribution or scientific Python in machine learning, at least. I think Peter was showing some demo about it a while ago,
Yeah.
years ago. It's Anaconda is big anyway. Anyway, but that's. I should stop giving compliments. I once contracted for Anaconda as well, so it's like I should mention it. But I use it. I use it for whatever I'm doing myself. So it's like anyway. Any more questions? If not, I have one more question for you, and then we'll let you go. Hopefully there are other questions other than mine. Okay, so since there is no question other than mine, unless someone has a question after that, I'll ask you the question because you said that you actually polled your users. What are they using Dask for? Sorry, Number for, not Dask. They're
Yeah,
using
so I
Number.
have that,
Yeah,
that
yeah,
Twitter thread very conveniently here. Let me actually paste this in if people want to follow along.
yeah, but tell
So
us something that you liked.
Oh well, so one that isn't in this list. I mean, although there's some very cool stuff in here. Climate modeling and image processing and stuff. There's an old use case that isn't listed here that I remember from the early days of Numba because they had some questions for us and asked things. And my favorite one was someone had written a I think they described it as a kite propulsion simulator. So basically, the idea that you can use very large kites mounted to cargo ships to supplement their engines and reduce the amount of emissions they produce and the fuel costs and all that stuff, to sort of use a hybrid of wind power in addition to diesel to run the ship. And so they had written a whole simulation of how this would work, I guess, a whole physics simulation. And they did this using Numba and had lots of great questions for us in the early days of Numba. I haven't found that project lately, but that was just one of the weirdest things I had ever seen. Very cool idea. But yeah, so that I thought was very neat.
Aha, cool. I like it. I like it already. I hope it returns.
Yeah.
Okay, so if there are no other questions, and I'll give you questions number going once, question going twice, questions going three times, no more questions. So I would like to thank you, Stan, so much for giving us a very nice presentation of Numba. I've been actually had to call you way before because I knew this language this library was here, but I never like it was kind of delayed, and I'm very happy that you made it and gave us this talk. So I would like everyone who can to unmute yourself and make some claps or in the chat make some noises. Stan, thank you very much.
Thank you.
Oh yeah, oh I see the
Oh,
claps.
wow, this software is fascinating. I didn't know you could do
Oh,
that.
now they're coming.
Okay. Thanks.
Okay. Well, we're gonna stop the recording now. Wait a second, don't go away.